So this lecture is about minerals. So if you remember, towards the end of the last lecture, I introduced Donna's mineral classification. And I told you not to worry about it because that's about the next lecture. So now is the time to worry about it. So don't worry about this list right now because some of these things are very important in the archaeology of stuff and some are not very important at all. So I'll go through them now, talking about them and giving examples and that sort of thing and telling you which are the important ones and which you should just forget about. Native elements are very important. These are simple minerals, theoretically of one element. They include metallics like gold and silver, and non-metallics like diamond and graphite. Gold, of course, is a very important archaeological material. It forms in quartz veins, and it doesn't combine with oxygen or sulfur. So none of that cationic bonding goes on with gold. It's always found in the native state. So this is why it doesn't rust. So iron will turn brown with oxygen. Copper will turn green with oxygen. Silver will turn purple. So these things all degrade and become not shiny. Gold is always shiny. So it's one of the things that makes it quite spectacular to find. It is, however, always alloyed with certain other metals, such as silver and copper. This is called electrum and was, in the time of Tutankhamun, this is this chap here, this would have actually been electrum. They didn't have the method of extracting the silver and copper from the gold at this time. So the next group are sulfides. So sulfides include some very important minerals like galena, PBS, nickelite, a very important source of nickel, pyrite, iron sulfide, a very important source of iron, argentite is one of the main sources of silver, chalcopyrite is an important source of copper, erythrite is an important source of cobalt, which you may be thinking, what's cobalt for? Well, cobalt's used to paint pottery blue, which we shall get to later on. Now, sulfides are associated in particular with hydrothermal vents, which come out of the seabed near spreading ridges where the magma comes up, and you have all this stuff coming out, all sorts of iron and chromium and copper and all sorts of very useful stuff. And so all these metalliferous sediments are deposited on the surface of the ocean floor, and then as it spreads and goes further away, it's still in here. And so then when you get things like the Zagros thrust and the Oman thrust and the Troodos Mountains thrust, you will get oceanic crust. If you remember from an earlier lecture, there was oceanic crust between the Eurasian plate and the Afro-Arabian plate, and so that's all got rocked up, that didn't get subducted entirely and is on the surface. And so this has all become very important sources of, for instance, copper. If you remember, copper were very important from Oman and from Cyprus. Oxides. Oxides are very important. They include the important ore minerals such as hematite and magnetite. So very important sources of iron. Corundum, aluminium oxide, also known as emery, which of course is a very hard material. Cassiterite is the main source of tin, And so for the very rare and important tin element, which is essential for true bronzes, you need to find cassiterite, which is quite rare. So about corundum, this is emery. So corundum is one of the hardest materials available. And so emery is actually a material which was used for working anything softer than this, particularly the harder materials like quartz. Halides are moderately important, have an anion of chlorine, fluorine, iodine, and or bromine. This is important in archaeology more than the archaeology of stuff, shall we say. Salt. Not a lot of things are made of salt. There are things made of fluorite, but they're not very common. Sorargyrite is quite important. It's, again, an important ore of silver. Ag is silver, you see. So moderately important, but not greatly important. Carbonates, on the other hand, are very important in the archaeology of stuff because they include calcite and dolomite. Go back here. So this is the carbonate. Carbon and oxygen together make a carbonate. So these in particular would have developed in the skeletons of many of these organisms you see in this reef here, and would have been deposited on the seabed and like this, and would have become minerals like rocks like marble. Calcite is quite soft, it's only 3, so you can work it with copper, and is very popular for making statues. It's easy to work, but still quite hard in the end, and is very amenable to what would have happened to most of these statues, painting to make them the color of the person, not white, like this person is. There are quarries for marble over a great deal of the Mediterranean. Some of these aren't actually, they're just Roman quarries, but a lot of them here and in Italy. You imagine, as I said in an earlier lecture, here is Greece and here is Italy. So this is actually oceanic bed at some stage, covered with limestone, which when all this slams into Eurasia, turns into mountains filled with marble. There's also travertine, which is calcite which is deposited by running water, like this. This is, let's go back to that. This is the source of alabaster in Egypt. There are 2 types of alabaster, which we'll get to, but one of which is this from Egypt, which is a calcite-based alabaster. Dolomite is from the replacement of calcite in the rock. You see the pink here is this is a thin section, is dyed because it's calcite, whereas this is dolomite, which has replaced it. Malachite is a carbonate. This occurs from the decay of sulfides, chalcopyrite, the copper sulfide found in places like Oman, will often have on the surface, it's been weathered and crystallized into malachite. So it's very easy to find, and malachite is very easy to turn into copper. You just put it in a fire and suddenly you have copper. So it's a very, and obviously very nice green mineral, easy to find when you can find it. It's not common, but you don't miss it. Also became very important paint. See the green bits? See the green bits? Gypsum. Gypsum is a sulfate. Gypsum is 2 on the Mohs scale of hardness and is another alabaster. You see, calcite is an alabaster and gypsum is an alabaster. They're both alabaster. This is the alabaster that came from Iraq, sometimes called Baghdad marble. And so this is what reliefs like this, these Neosyrian reliefs, quite well known, certainly if you ever go to the British Museum, like this one. And this is made of gypsum. Also very important for making lime, which we shall get to in a future lecture. Phosphates. This include apatite, which is a very useful mineral, and fluorapatite, which is the mineral which grows in your bones. Not a very important source of raw materials for making archaeological things, but quite common type of rock. Phosphatic deposits, phosphatoids as they're known, are from the deposits like this person died, or this fish actually. This fish died and its bones were deposited at the bottom of the ocean and turned into phosphatic rocks, just as all these shelly organisms turned into limestones. As you can see, there's a lot more limestone than there is fish. Phosphates also include a very important mineral called lazulite, which is the blue component of lapis lazuli, which was particularly important in Mesopotamia when they were making cylinder seals and other things, which we should come to later on. So from about 2750 BC, I don't know which reckoning that is, but around there, lapis lazuli is found in large quantities in Mesopotamia, and it all comes from Afghanistan. There's to this day a massive mine at a place called Barakshan in Afghanistan, where they get just about all of the world's lapis lazuli. And although there may have been other sources, this is probably where it came from back in Mesopotamia. One of the things about lapis lazuli is that it's actually made of 3 minerals typically, and they would actually talk about this in ancient Mesopotamia. There's the blue bits, but also the white and the sparkly gold bits. The white bits are actually calcite, they're like marble, whereas the sparkly bits are iron pyrite, iron sulfide. And so they would often talk about these things as being blue and white and sparkly like gold. So lapis lazuli is actually a combination of something which is quite hard, lazulite. You cut it with steel easily enough, but calcite is 3. So silica. So silica, of course, one of the most common materials on the Earth's surface. Some of it is quite pure silica, quartz. Quartz is quite important. There are macrocrystalline varieties, like quartz crystals, like this crystal quartz, and cryptocrystalline or microcrystalline varieties, like chalcedony and agate, and also chert and flint, which are very important, of course, for making things. So chert around the world is a very common material for making lithics with, because of its nature, which is responds equally in all directions. So silica, like that, actually is deposited in reefs like this. See, I think that's a sponge. Sponge has silica in their skeleton. So you have calcareous skeletons, you have phosphatic skeletons like you and I have, and you have siliceous skeletons like sponges have. And so these are deposited when they died and become silicic deposits, which turn into chert and flint. You also get a lot of silica in sandstones, and this is a good example because it isn't. Only these more whiter bits are actually probably silica. These other darker things are something else. But still, most of the sand you find is silica, because with time sediments become more mature, as it's called by sedimentologists, which basically mean all the softer minerals are worn away and what you have mostly left is silica. So all the the main beaches, like in the Middle East, or the sand dunes, are mostly made of silica sands. Now, the silica tetrahedron, which is this thing, is made up of 4 silicas and four oxygens and a silica. SiO4, you might call it. And these string together. So you imagine this triangle is actually this, like this, you see. And so you'll have the oxygens linking together and forming chains, and forming other chains, and forming networks. And so that creates all this type of silicates, which you should promptly forget, because there's a lot and it's of limited relevance to the archaeology of stuff, all except one of them: phyllosilicates. So you should be able to remember this. Just think of the pastry. Phyllosilicates, sheet silicates, which are just as useful as a nice dessert made of sheets. Very similar. This become very important later on, of course, because things like clays are phyllosilicates. And to understand what pottery is, and understanding what pottery is quite useful for archaeologists, it being one of the most common artifact types. It's essential to understand clays to understand pottery. So, as I say, don't worry about the silicates, but some of the minerals you should know. Olivine is a nesosilicate, which just has lone tetrahedra in between iron and magnesium. And so this is olivine, very nice green mineral. This is actually a bit of the mantle, which has been blasted up to the Earth's surface. So this is all down there. All of this is olivine. And so at the top, there's more siliceous, but at the bottom here, it is more olivine. And so this is pure olivine down here. And so you'll get a lot of this whenever you get the Earth's, the crust of the sea, the oceanic crust, being thrust up onto the Earth's surface. You will get olivine. It is, however, tends to be altered and metamorphosed into another mineral. But it's very simple: iron, magnesium, and silica. So olivine here is very characteristic of ultramafic igneous rocks. And so we shall talk a bit about that when we get to igneous rocks. So here the ultramafic, filled with iron and magnesium, are the ultramafic rocks over here. So sorosilicates, double tetrahedra, include epidote, which we won't worry about, but it's quite important for metamorphic rocks because there's a certain relationship between pressure and temperature. You get epidote forming. See the epidote here? Cyclosilicates include the very attractive but not especially important tourmaline, one of my favorite minerals. So all you need to know about that is really nothing really. But it's got boron in it, so it's one of the very few. But it's not boring, it's very pretty. Inosilicates, single chain, include the pyroxene group, which I've talked about before, a complex ferromagnesian aluminosilicate. This is it, very common in basalts, and also is what jadeite is. Jadeite axe here, you see. These are also important in rock-forming minerals. This is gabbro or basalt, so this is mafic rock, has a lot of pyroxene in it, and some plagioclase and sometimes some olivine, but it's mostly pyroxenes. The amphibole group are inosilicates, so again, complex ferromagnesian aluminosilicates with water in it. See, the pyroxenes had no water. They include hornblende. This is hornblende, one of the more complicated amphiboles. And that's what they are, complex hydrous ferromagnesian silicates. And they are the dark bits you see in granites quite often. So in granites, like this is the well-known Aswan granite, you have pink bits, you have white bits, and you have black bits. And most of the black bits are actually amphibole. Amphiboles are also important in metamorphic rocks, where here you can see rocks which have quite high temperature but low pressure have a lot of amphiboles in them, sometimes entirely amphiboles. One particular important amphibole is nephrite, which is the type of jade found in ancient China. Phyllosilicates. Told you they were important. So this is the only silicate type that gets the green arrow because it forms tasty sheets of mica. For instance, mica is a quite important type of mineral. Muscovite is one of them. Potassium, aluminium, aluminosilicate with water in it. Water, is it? And biotite is the one with more iron in it, so it's actually black. Serpentine. Serpentine is actually quite an important mineral, which we get things being made out of. It's magnesium, silicon, and oxygen, and with water in it. So I was mentioning earlier magnesium, silica, and oxygen, about how, oh, and here's some of the important things made out of it, cylinder seals. It's made of olivine. Okay, so here you have the oceanic ridge, and you have these olivine-rich rocks here. And so what happens to olivine once it's thrust up to the surface is it gets water in it and loses iron. So you can imagine, so this is serpentine, magnesium, silicon with water in it, or hydroxyl, but water is close enough. And so it loses its iron and becomes all green and squishy, quite soft, or softer than this, which is quite a hard mineral. And so this produces, of course, a lot of iron. So you'll often find that these minerals, serpentine, are associated with important deposits of iron and copper. Don't forget, copper is found because of the sulfides on the surface here. And so if you have serpentine, you have control over these important sources of iron and copper. Chlorite is quite important. It's another phyllosilicate. This forms quite often quite soft. You can scratch it with your fingernail. And chlorite schists, greenstones often called. Lots of things are called greenstones, so for God's sake, don't ever use that term. Very important for making things out of, particularly in Iran. And some of this went to Iraq. This is probably Iranian chlorite schist, and like that. This little Western Iranian stamp seal is also made of chlorite schist. Talc, very soft mineral, magnesium silicate with water in it. All of the phyllosilicates have water in it, or hydroxyl. And this is what makes steatite, another rock type which is maybe better known if you've ever had to do a soapstone project in school. Soapstone is also silicate, steatite, which is also talc. It's very, very soft, a hardness of like 1, and so it's very easily worked. So what they would often do is fire it. And so you would work the very soft talc, and you fire it, and it loses its water and becomes enstatite, which is a pyroxene. And so you can see it goes from a hardness of 1, and you put it in a fire for a bit, and it becomes a hardness of 6, which is pretty hard, really. So then, of course, we come to the very important group of phyllosilicates, clays, of which the easiest to understand is kaolinite, because it's very simple aluminium, and silica. Aluminosilicate with water in it, like all phyllosilicates have some water in it, as far as I'm aware anyway. Certainly all the ones I'm talking to have water in it. Then there's the morylonite smectite group. See, these don't get an arrow because who's going to remember morylonite and smectite? Illite. So very important clay groups, but, you know, don't worry too much about it. So this is the structure. So you have the silicon tetrahedron, 1 silica and 4 oxygens, and the aluminium octahedron, which is aluminium and oxygen. So these two together can link through the oxygens to form these sheet-like structures. And this is actually the structure of kaolin. So it's worth knowing kaolin because it has the simplest structure and easiest to understand. And so you can see it has the aluminium here, the silicon here, and here, which we shall call water, is here. And so this is an integral part of the structure of kaolin and all clay minerals. And the other clay minerals are like really complicated up here, so it's going to be confusing. So what happens with pottery is that there's a lot of clay in the material that you make pottery from, and then you fire the clay. Firing destroys the water. It drives the water away and destroys the structure of the clay. And so that's why there is so much pottery, because once you've turned this clay into pottery, you can't recycle it. It's not like other materials where you can melt it down and reuse it. Once it's been fired, it's stuck that way forever, and you can't like reuse that material for anything else, except possibly if you crush it and put it in other pottery and stuff like that. And so that's why all the pottery that's been made still has the potential of being out there somewhere, and is why it's one of the most common of archaeological artifacts. But of course, we have like lectures and lectures about pottery. So, oh yeah, there it is. Pottery, yeah, that's warning you about all the lectures about pottery. So you have now tectosilicates, which have a 3D framework, and the most important of these are the feldspars. Feldspars are very important rocks. There is the potassic feldspar orthoclase, potassium aluminium silicate. That's the pink bits. See, this is again Aswan granite, or this is actually at Tadmor Palmyra in Syria, and that's what the pink bits are. Other feldspars include plagioclase, which is actually a solid solution series. You see, aluminium silica and either sodium or calcium, and it goes from one to the other. This is the common rock type in basaltic rocks. So here you have a gabbro, you have a basalt, and that's what all these little white bits are. And here you can see lots of plagioclase in the intermediate and mafic igneous rocks. So that's the white bits. It's all black and white. So that's minerals. Well, for now, anyway. So next week, or next time, we shall have something else. Thank you.